First of all, I would like to introduce myself. I am Jenő Gubicza, professor at Eötvös Loránd University, Budapest, Hungary. In my presentation, I would like to talk about machine learning-based mapping of the nanostructure in a combinatorial multi-principal element alloy. This research was performed in cooperation of 4 research institutes: Eötvös Loránd University, Hungary, EMBA Institute, Switzerland, ETH, Zurich University, Switzerland, and DAISY Synchrotron, Hamburg, Germany. In conventional solid solutions, there is one principal element and there are additional alloying atoms which are added in order to improve the properties, for instance to increase the strength. About 20 years ago, a new type of alloy concept was developed, multi-principal element alloys, acronym is MPEA. The MPEAs contain 3 or more elements with equal or near equal fractions, therefore their compositions corresponds to the unexplored middle parts of the phase diagrams. At the right side of the slide you can see a schematic of a cobalt chromium iron nickel phase diagram at a certain temperature, for instance at room temperature, and in the middle you can see a sphere which represents the unexplored middle part of the phase diagram, which corresponds to the multi-principal element alloys in this alloying system. In multi-principal element alloys there are no solvent and solute atoms, that is, all constituents have similar roles in the alloys. In multi-principal element alloys, very often a single-phase disordered solid solution form due to the stabilization effect of the high configurational entropy. At the right bottom side of the slide you can see a schematic of a 6-component multi-principal element alloy: aluminium, cobalt, chromium, iron, nickel, titanium. You can see the disordered solid solution lattice, and the figure revealed a distortion in the lattice due to the different sizes of the constituent atoms. As I have mentioned, the configurational entropy can stabilize the single phase disordered solid solution structure in multi-principal element alloys. If the constituent fractions are equal, then the configuration entropy can be expressed as the product of the universal gas constant R and the logarithm of the number of elements n. The higher the configuration entropy, the lower the Gibbs free energy, as can be seen in this equation. Therefore, the higher configuration entropy can stabilize the structure. At the right side of the slide, you can see a plot showing the configurational entropy versus the number of elements for equimolar alloys. You can see that there is a monotonous increase of the configurational entropy, and if the number of elements is higher than 5, then the configuration entropy is higher than 13 joule per Kelvin per mole. These multi-principal element alloys having higher number of principal elements than 5 are called as high entropy alloys. So the high entropy alloys contain 5 or more principal elements in equal or near equal atomic fractions. Up to now, several hundreds of multi-principal element alloys have been developed, and among them there are single and multi-phase materials. In material science there is a great interest in multi-principal element alloys because they have new property combinations. For instance, the high strengths can be combined with a good ductility. This plot shows the specific strengths, that is the strengths divided by the density of the different materials, and you can see that multi-principal element alloys, which are indicated by the spots, have very high specific strengths. In addition to the high hardness and strength, the multi-principal element alloys have good resistance to thermal softening, to oxidation, wear, and corrosion. The high strength of multi-principal element alloy is caused by the strong resistance of the disordered crystal lattice due to oscillation motion. Moreover, body-centered cubic multi-principal element alloys have high strength even at high temperature. These figures show the yield strength versus the temperature for 2 multi-principal element alloys containing niobium, molybdenum, tantalum, tungsten, and vanadium. and 2 commercial nickel-based superalloys. You can see that above 800 centigrades, the strength of the multi-principal element alloys is higher than for the nickel-based superalloys. The excellent resistance to thermal softening is caused by the sluggish diffusion in multi-principal element alloys. Due to the large variety of the selectable chemical elements, many different multi-principal element alloys can be produced. For a selected group of constituents, their concentrations can also be varied, resulting in different microstructures and properties. The effect of the chemical composition for a selected group of elements on the structure and properties can be studied using combinatorial samples. For instance, these 4 figures show X-ray fluorescence spectroscopy results on cobalt chromium iron nickel multi-principal element alloy film. The lateral diameter of the film was about 10 cm, and due to the different positions of the targets used in the sputtering when the film was produced, there was a gradient in the concentrations of the 4 constituents. The 4 graphs shows elemental maps on the multi-principal element alloy film. The mentioned multi-principal element alloy film was produced by multiple beam sputtering physical vapor deposition. This schematic on the slide shows the configuration inside the PVD chamber. An argon ion beam was used for the evaporation of the atoms from the target, and these atoms are deposited on the surface of the wafer, which was a single crystal silicon substrate. The vacuum in the PVD chamber was about 10 to the minus 7 millibar, and the deposition time was about 20 hours. At the bottom of the slide, you can see a photo on the PVD chamber, and you can see the 12 targets. Due to the 4 constituent elements of the PVD film, 3 targets were used for each constituent element. That means that 3 targets were made of cobalt, another 3 targets made of chromium, and 3 targets were made of iron, and other 3 targets were made of nickel. The targets made of the same element were placed next to each other. At the right bottom corner of the slide, you can see a photo on the finally obtained PVD film, for which the diameter was about 10 cm. X-ray fluorescence spectroscopy and transmission electron microscopy revealed that the thickness of the cobalt chromium iron nickel PVD film was about 1 micrometer. This TEM bright field image shows a cross-section of the film, and you can see that the film thickness is about 1 micrometer. At the right side, the dark field image revealed that there is a nanocrystalline microstructure inside the film, and the grains contain many twin folds. Fast structural mapping of the combinatorial sample was carried out by X-ray diffraction using synchrotron radiation at DZ Synchrotron Hamburg, Germany. XRD patterns were measured at about 1000 locations with different chemical compositions, which took about 2 hours. At the right bottom part of the slide, you can see the experimental setup with the sample and the detector. At the left side, you can see 2 diffractograms taken at 2 different locations. The upper one shows a point where the structure was fully FCC, and at the bottom you can see a double phase structure with ACP and FCC phase components. This figure shows the phase map obtained for the cobalt chromium iron nickel multi-principal element alloy film using synchrotron X-ray diffraction. At the 4 corners of the map, you can see the 4 constituent elements symbols, which indicate the approximate positions of the targets used in the PVD technique. Each element symbol indicates the 3 targets used for that element. The different colors in the map show the different structures identified by the X-ray diffraction patterns. The largest region, the largest zone, is related to the single face-centered cubic structure, but there are structures with double face components, hexagonal cross-packed and face-centered cubic, or face-centered cubic and body-centered cubic structures. The creation of this map is not very time-consuming procedure, because when we studied the evolution of the X-ray diffraction patterns, when we are moving from point to point, we can recognize the appearance of the new peaks when there is a phase transformation, there is a phase change, and therefore we can identify the boundaries between the different phase zones very easily. The question may be that whether beside the crystal structures, the microstructure also varies when the chemical composition changes. The construction of a microstructure map is also feasible using the X-ray diffraction patterns, because the X-ray diffraction peak profiles can be used for the determination of the parameters of the microstructure. This method is called X-ray line profile analysis. For an infinite defect-free crystal, the XRD peaks are Dirac delta functions. On the other hand, due to the finite crystallite size and the lattice defects such as dislocations inside the grains, the diffraction peaks are broadened, and the parameters of the microstructure can be extracted from the analysis of the peak profiles. X-ray line profile analysis can be carried out conventionally by a pattern fitting method. Such a method is the convolutional multiple hole profile fitting procedure. In this case, the experimental pattern is fitted by a theoretical function. For each peak profile, the theoretical function can be obtained as the convolution of the instrumental pattern, the theoretical profile for the crystallite size, the theoretical profile for the dislocations, and the twin faults. X-ray line profile analysis provides different parameters of the microstructure: the crystallite size distribution, the density of dislocations, the dislocation arrangement parameter, which characterize that whether the dislocations are clustered or not. If the dislocations are clustered into dislocation dipoles or Loenger-Green boundaries, as can be seen in the middle of the slide, then the value of the dislocation arrangement parameter is small. If there is no such a clustering of dislocations, so the dislocations are more or less distributed uniformly, then the M is large. M is the dislocation arrangement parameter. In addition, we can determine the type of dislocations. For cubic crystals, the edge or screw character of dislocations, and in hexagonal crystals, the population of basal, prismatic, and pyramidal slip systems. In addition, we can determine the twin fault probability, which gives the fraction of the crystal planes occupied by twin boundaries. However, the evaluation of 1000 patterns in the case of a combinatorial multi-principal element alloy film. So this evaluation of this huge number of patterns takes weeks using the conventional pattern fitting. Therefore, a much faster machine learning based X-ray line profile analysis method was developed for mapping the microstructure in the combinatorial multi-principal element alloy film. This flowchart shows the machine learning based X-ray line profile analysis procedure developed for the evaluation of X-ray diffractograms for FCC structures. The first step was to produce a learning set of X-ray diffractograms. For this purpose, we wrote a software which generated the X-ray diffractograms for any selected combinations of the microstructural parameters. The number of the calculated patterns was about 100,000. Then this learning set was used for training the model. The teaching was performed using gradient boosting implemented in the XGBoost library. After the training, we validate the model using a control set of diffractograms. So the control set of diffractograms was evaluated by the machine learning method, the trained machine learning model, and the microstructural parameters obtained from this evaluation were compared with the parameter values used for the creation of the control set of diffractograms. When there was a good agreement between the two sets of microstructural parameters, then the model was validated, and then we started to evaluate the X-ray diffractograms measured on the multi-principal element alloy film. First, there was a pre-processing of the measured dataset, in which there was a background subtraction using the AR-ELS method. Then the pre-processed diffractograms were evaluated by the machine learning based X-ray line profile analysis method, and the final results were validated, where we compared the microstructural parameters obtained by the machine learning method with the parameters obtained by CMWP conventional fitting, but of course this comparison were made only for some selected points in the multi-principal element alloy film. The number of these control points, comparison of points, was about 10. As I have mentioned, before we used the machine learning method, we validated the model. That means that we compared the microstructural parameter values used for the calculation of the control set of X-ray diffractograms and the predicted microstructural parameter values obtained by the new machine learning based method. This figure shows the comparison of the dislocation density values obtained by the machine learning method. This is on the vertical axis, and the real dislocation densities used for the calculation of the control set diffractograms. You can see a very good agreement. So similar agreement was obtained for the other microstructural parameters, and this validated the used model. And now let's see the results obtained by the machine learning based X-ray line profile analysis. First, I show the crystallite size map obtained for the FCC region. You can see that the crystallite size varied between 9 and 36 nanometer. So this is a nanocrystalline microstructure in accordance with the TEM results. The lowest crystallite size, which was about 10 nanometer, was observed in the middle of the disk, where the concentration is at least 10% for each element. That is, the alloy consists of 4 major components. This is the dislocation density map for the FCC region. It is clear that the dislocation density is very high, varied between 85 times 10 to the 14 1 over square meter and 460 times 10 to the 14 1 over square meters. The largest dislocation density, with a value of about 300-400 times 10 to the 14 1 over square meter, was obtained in the upper part of the FCC region, with the chemical composition of about 30 atomic % cobalt, 40 atomic % chromium, 10% iron, and 20% nickel. This is the twin-fold probability map for the FCC region, where you can see that the twin-fold probability varied between 0.6 and 4.2%. In the upper part of the FCC region, the twin-fold probability was very high, the highest, with the value of about 4%. The running time of the whole procedure, the whole creation of the maps, is on the order of hours, which is comparable with the acquisition time of the X-ray diffraction patterns using synchrotron radiation. So this is very fast. Most of this time is taken by the production of the learning set and the training of the model and the determination of the microstructural parameters. So the creation of the maps required only some seconds. So it is a very fast method. The novel machine learning based X-ray line profile analysis method was shown in detail in a publication appeared in the journal Nanomaterials recently. It should be noted that the new machine learning based X-ray line profile analysis method was elaborated only for single-phase FCC materials, and further development is required for its extension to other structures such as hexagonal closed packed or body-centered cubic structures, and additionally to multi-phase structure. In summary, I can tell that a novel machine learning based X-ray line profile analysis method was developed for the characterization of the microstructure. This method is much faster than the conventional pattern fitting methods. The new machine learning based X-ray line profile analysis method was successfully applied for mapping the microstructure in a combinatorial cobalt, chromium, iron, nickel, multi-principal element alloy film. Finally, I would like to draw your attention to my books related to this topic. The first one is about the X-ray line profile analysis method, and the second one is about the defect structure and properties of nanomaterials. Thank you very much for your kind attention.